Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and this is part 2 of related rates. In the last video, we talked about how we work with related rates problems. If the function isn't given, you have to start there and come up with a relationship between the variables they're discussing. Then you determine what rate of change or time rate of change is given and which one is asked for and any other values that you're given. You then differentiate your function with respect to time, every term with respect to time, treating every variable as a function of time and therefore using the chain rule. Then you plug in the values that you know and hopefully you're left with one unknown that you solve for. So I want to take a look at 3 examples in this video of typical related rates questions you may see. So let's get started. In this first question, it's one of the gas laws. It says the pressure of a gas varies inversely as the volume. And then it tells us that the volume is 500 cubic centimeters when the pressure is 200 kilopascals. And we know that the volume is increasing at a rate of 15 cubic centimeters per minute. It's asking us how fast is the pressure changing when the volume is 750 cubic centimeters. There's a lot of information here and a lot of numbers. So let's just break it down. We're told the pressure of a gas varies inversely as the volume. So let's write that as an equation. That's an inverse variation. So pressure varies inversely. K is my constant of proportionality. Anytime you're working with direct proportion or inverse or a combination of those, you're going to have a constant of proportionality over volume. So pressure will equal a constant divided by volume. In other words, with an inverse proportion, your product of pressure and volume will equal a constant. But I'm going to write it pressure as a function of volume. So let's determine our rates of change, what we know, what we need to find, and any other values. So we're told this rate of change and we're asked to find how fast the pressure is changing. So we know dV dt is increasing, so it's a positive 15 cubic centimeters per minute. And it's asking us to find how fast the pressure is changing, so dP dt when the volume is 750 cubic centimeters. Now, before we start this question, we need to find this constant, and that's where we're going to use this information here. If P is equal to K times V, that means pressure times volume is equal to our constant. So let me just move this over. Before I differentiate this, I have another unknown value. It is a constant value, but I'm given this and this that will allow me to find that. If pressure is equal to constant divided by volume, then that constant will equal pressure times volume. So I know that the pressure is 200 when the volume is 500. So my constant in this example is going to be 100,000. So my function is 100,000. Now another thing I'm going to do, I don't want to use the quotient rule when I differentiate this, and I don't need to because my numerator will be constant. So I'm going to write that as 100,000 times v to the negative 1. So I found K, and then I brought volume out of the denominator by giving it a negative 1 exponent. Now I will differentiate this dP with respect to time, so dP dt will equal 100,000 times negative 1 will be negative 100,000 times v to the negative 1 minus 1 is negative 2. And remember, v is a function of time, so I'm differentiating with respect to time, so times dV dt. I can now find dP dt by plugging my values in. So I don't need these values anymore. I didn't want to know how the pressure was changing at those values. I wanted to know how it was changing at this value. So I ignore those, I just use those to find my constant. So dp dt will equal, I'm going to plug my values in. So the volume is 750, v to the negative 2, so that would be like 1 over v squared, so 1 over 750 squared, times dv dt is 15. And when I multiply all of that, I get a value of negative 2.67. Pressures is measured in kilopascals. My time factor is per minute. And it makes sense that my pressure should be decreasing as my volume is increasing. It is an inverse proportion. So as one increases, the other should decrease. Let's take a look at another example. In this next example, it says a cylindrical oil tank, and we're going to assume standing upright, with a radius of 2.5 meters and a height of 10 meters is being filled at the rate of 7.5 cubic meters per minute. How fast is the oil rising when the depth of the oil is 2 meters? So we're talking about the size of a cylinder. We need to use volume of a cylinder. Volume of a cylinder is pi times radius squared times height. Now we have volume as a function of 2 independent variables. So we have 3 unknowns in this case. When you have 3 unknowns, you look to see if any of those values is remaining constant. If the oil is coming into the tank at a certain rate, the height is changing, the volume is changed, the volume of the oil is changing, but the radius stays constant. So we know the radius, therefore we're going to plug it in and not think of it as a variable. When you know one of the variables is constant, the easiest thing to do is put that value in right at the very beginning before you even differentiate. So we know that dv dt is 7.5 cubic meters per minute. The question asked us to find how fast the oil is rising, so that would be h. We want to find dh dt. How is the height changing when the height or depth is 2 meters? All of our units are consistent, so we can go ahead and differentiate. Again, volume and height are changing with time, so we differentiate with respect to time. So the derivative of v with respect to t is dv dt equals 6.25 pi is just a constant, times the derivative of h with respect to time is just dh dt. We want to find dh dt, so dh dt will be equal to dv dt divided by 6.25 pi. And now I'll plug my values in. dv dt is 7.5 cubic meters per minute. And when I calculate that, I get 0.382 meters per minute. We get meters per minute because height will be measured in meters, and we know our time factor is per minute. Notice that we didn't even need to use h, and that's because we have a right solid, the sides go straight up, so the rate of change of height is going to always be the same. It doesn't matter at what depth. Let's take a look at another example in this video where we have 3 variables again, but none of them remain constant. In our next example, we have Barney and Fred leaving the same destination at the same time. Barney travels east, so here's our destination. Barney travels east, so we'll call that B, and at the rate of 60 kilometers an hour. And Fred travels north, I'll call that A, at 80 kilometers per hour. How fast is the distance between them changing? So that would be this distance between them here. So we want to know how fast is this changing. I'm going to call that C. So I want to know dc dt, and I know db dt, and I know dA dt. 1.5 hours later. So first of all, I want a relationship between A, B, and C. We now have 3 variables and none of them are remaining constant. So I have to write my equation in terms of those 3 variables. So A squared plus B squared will equal C squared. And I know 2 rates of change, and I'm asking to find the 3rd rate of change. So if all 3 variables, if you do have 3 variables and all 3 of them are changing, in order to find 1-time rate of change, you need the other 2, so we're okay. When we differentiate, remember all of these values are changing with time, so I'm differentiating with respect to time. I will get 2a dA dt plus 2b dB dt will equal 2c dC dt. Let's divide through by 2, so I'll have a dA dt plus b dB dt equals c dC dt. So I have my rates of change, these 2, and I want to find this one. But I also need to know A, B, and C. And in order to find those, I use my time. I can find how far Fred has gone in 1.5 hours. I just take Fred's rate times 1.5. So A will equal 1.5 hours times the rate or speed of 80 gives me 120 kilometers. I do the same thing for B. In 1.5 hours, Barney will have gone 60 times 1.5, which would be 90 kilometers. And in order to find C, I use my right triangle theorem. So to find C, when A is 120 kilometers and B is 90, I plug into A squared plus B squared equals C squared, and I will get 150 kilometers. A is 120 times dA dt is 80, and they're all positive values. B is 90 times BD dt is 60 equals C, which is 150 times dC dt. That's what I need to find. So when I multiply these, add them, divide by 150, you can try it on your calculator, you will get a value of 100 kilometers per hour. I'm picking easy numbers because the concept is difficult enough without messing it up even further with more complicated numbers. But the process is the same, and you have calculators so you can easily calculate it. It's just I like to keep it fairly simple with easier numbers when I'm demonstrating the examples. But in the real world, you're going to get numbers that aren't quite so nice and neat. So it is possible to differentiate when you have 3 unknowns. As long as you've got 2 rates of change, you can find the missing rate of change. I want to do 2 more examples, and they are what I would consider the most challenging related rate type questions. So that's going to be on the next video. In the meantime, practice as many of these as you can, the ones I did in the previous video plus this one. And when you're ready for a challenge, then take a look at the next video. Take care.